Alright, and welcome to this video where I'm going to practice using splitting the sum and binding the term to find upper and lower bounds on a couple of sums here. Alright, I'm going to write our first sum here as I to the 1/2 instead of square root of I. That's just going to make it a little bit easier for us to see a pattern as it starts to appear as we do these problems. And I think I'm going to also start here with my upper bound, so that means I'm going to do a less than or equal to for my first one. Now remember the technique as we introduced it in the last video. We're going to overestimate our term here. The square root of I is an increasing function, so the largest it will be is when we get to square root of n. So rewriting that here, over approximating our term I, replacing the I with an n basically, we get this term here, and then we can complete our math pretty simply here. The n to the 1/2 comes out front, and we have a very easy sum to compute. We get n to the 1/2 times n, which is n to the 3/2. And again, that's a really good guess for our bound, n to the 3/2. And again, we've shown big O with our upper bound here, and remember our b out front here is a 1. So we've applied the definition of big O with the less than or equals to b times n to the 3/2. So we've shown big O here. So now we want to do big omega, and big omega means we're going to do our lower bound. So we're now looking for the lower bound with a greater than or equal to. And again, if we just use the binding the term technique here, plugging in the 1 here for our I, we'll get 1, well, the square root of 1. We're actually going to do a little better than in our previous example. We're going to end up with an n total. But our n, again, doesn't match our upper bound. We need to match n to the 3/2, and so that's not a tight bound. So we definitely need to use our other technique, our splitting the sum technique. So I do want to use the splitting the sum technique. And so remember what we're going to do in the splitting the sum technique is we're going to replace the whole sum, or approximate the whole sum, with half the sum. So instead of starting at 1, we'll start around the middle point, the floor of n over 2 plus 1. And again, I've chosen this point, the first half of the sum up to the floor of n over 2 we've thrown away. I've chosen this point. The plus 1's actually going to cancel out with a minus 1 in a little bit, which makes it sort of nice. That's why we're actually going to keep it around instead of maybe trying a different point to split. All right, so continuing on here, we're now going to under approximate, or we're going to use the binding the term technique to replace our I here with this value, the lowest it is. Again, keeping in mind that I square, or the square root of I, is an increasing function. So the smallest this sum gets is when we have the first value. So I'm going to write this here in brackets. All right. Now again, that looks a little bit nasty. We've got some stuff inside of a square root, but trust in the math, and it's hopefully going to cancel out and make things a little bit easier in a second. So again, 2 steps of approximation here. First one, splitting the sum, replacing all the terms with half the terms. Second step, we're taking this I and replacing it with its lowest value. So now we're here. Now after those 2 steps, we can factor this out front, so we no longer need to keep it there. So we now have all out front. We still have our sum. And remember, in our previous video, we did determine what this value is equal to. This sum, the whole sum, and maybe I'll just write it here, is just the ceiling of n over 2, the whole sum here. And then what else were we left with? This other term that I left here. We got it all to the 1/2. Okay, so not that bad. Let's continue down here. Now, again, keeping in mind the notation I used, these 2 steps were algebraic steps, so I used equals. These 2 steps were approximations, so I used greater than or equal to. But the next step I'm going to use, I'm also going to do an approximation. I want to start getting rid of my ceilings and floors. And again here, keep in mind, the ceiling of n over 2 is always greater than or equal to n over 2. That's just an easy one. We can drop it off on this direction. But the floor of n over 2 is greater than or equal to n over 2 minus 1. So the minus 1 is going to cancel with the plus 1. I promised you that was going to happen. So that's going to leave us here with n over 2 to the 1/2. So the final result is n over 2, the whole thing, to the 3/2. Now notice this is big omega now of n to the 3/2. The value we have here, it's maybe a little bit harder to see, but it's 1 over 2 root 2, or 1 over 2 to the 3/2 is the value of a that we have in our proof for big omega. All right, I'm going to do another one here, the sum from I equals 1 to n of I squared. And again, maybe I'll start with my upper bound here. Some of you, maybe if you've already studied your summations in a little more detail, you might already know what this is equal to. I must confess, I know that it has a closed form, but I've never actually memorized it. I probably could make a guess at it right now, write down some numbers. I know there's a 3, a 2, and a 6 in there. I might mix up which order they go. That's part of the reason why I don't know what it is because as a computer scientist, I rarely need to know what it exactly is equal to. More often than not, I'm okay with just knowing what an upper and a lower bound is, and I already know what my upper and lower bounds are on it, so that's probably why I've never committed it to memory. So let's maybe go through it ourselves, and then maybe we will not need to commit it to memory either. So I'm going to do the upper bound first. And here we are following the same technique. I'm going to replace that I squared with an n squared, making it as large as I can. And then we're just going to get some pretty straightforward steps now that we've practiced a couple times now. Okay, again, the n squareds come out front. We're left with just a 1. And then obviously that whole thing's just going to collapse. This becomes another copy of n, so we're up to n cubed now. And again, maybe n cubed would be a good guess. And hopefully, if you've been practicing along and following along here, you're starting to see a pattern, and maybe you can go ahead and start filling in that pattern yourself in your own toolkit so that you have maybe some more intuition about what you're going to see. So again, we want to tackle this problem, but on the lower bound now. So on the lower bound, we're going to be doing greater than or equal to. And again, I need to use splitting the sum. Let's just verify that if I plug in my 1 for all these terms here, they'll all just turn into 1s. So we'll actually only get n 1s. And my lower bound again will be n. Well, n is not a good lower bound for n cubed. That's not a tight lower bound. We want one that matches. So if we want one that matches, we are again probably going to have to use our splitting the sum technique. So let's split the sum. Again, that's the first step. That makes it possible for us to now under approximate that term. So my I squared term, going to be careful here. Floor n over 2 plus 1 all squared. Again, 2 approximation steps to get to here. Now we need to do a little bit of algebra and maybe one more approximation at the end to get rid of our floors and ceilings. So a little bit of algebra we're going to factor out. Again, we've now seen this sum 3 times, and again it's the ceiling of n over 2. And we're left with this term still that we need to bring over. So that's going to be the floor of n over 2 plus 1 all squared. Again, if you've sort of got your notes, you can see we've got a very similar pattern to the last example. Okay, continuing on. Oops, I put another equals, but this is time for another approximation step where I want to get rid of my ceilings and my floors. So get rid of my ceiling here. Remember, the ceiling of n over 2 is just straightforwardly greater than n over 2 itself. Maybe I'll leave that in brackets just to keep mine separate. Same thing here. The floor of n over 2 is greater than or equal to n over 2 minus 1. The minus 1 and the plus 1 again cancel out. That's been happening in all our examples. So again, we have an n over 2 here, but this one's raised to the power of 2. So it looks like we get n cubed. That's what we were hoping for. But now I'll just expand it out here over 8. Again, giving us our big omega of n cubed. So big omega matches our big O. That's good. Remember, that's sufficient then, the two of them together, for big theta. So we've now shown our sum is in big theta, and that's what we're hoping for. Maybe I will finish, because this is sort of an important, worth noting, that we've gone ahead and done a proof on this sum now. We did an upper bound. We said that this is less than or equal to n cubed. That was the value we got up here. And our value out front was a 1. And then on the bottom end, we still had our n cubed. But, maybe I'll write it like this, it's 1/8. So we found, we've come up with a description, or we've come up with an estimation of what this sum is going to be equal to. And maybe it might be worthwhile for us to think a little bit of what that's going to look like. So here I made a cube. Now this cube, if we had n, and where's my other n need to go here? If this is a n by n by n cube, right, then the volume of that cube is this. Okay, so we're saying the sum of all these squareds that we were interested in is less than this area. Okay. Now, what's 1/8 of this area? Well, when we're working with cubes, 1/8 is this little quarter. If we split off all our dimensions by 1/2 here, we're actually going to get 8 cubes, 4 on the bottom, 4 on the top. So one of those little ones, that's 1/8 of our n cubed. So the estimation that we've got here is if we were to draw these two cubes, our sum has volume somewhere between these two. And what it is, well, maybe that's a good enough approximation for you. It's good enough for us to say it's n theta of n cubed, so maybe that's good enough. But maybe we'll want a tighter one, and probably in my next video I will show us a way to get a tighter bound than even this if we needed it. Alright, so I've included this one in here. I log I. What would you do if you had to deal with something like this? Now, there's more than one way to tackle this. In a later video, I'm going to show again an example where we need to get a real good approximation on this. But I might want to, again, just practice the techniques we've been using. But maybe let's test our intuition here. We've already done a couple. We just finished one that was the sum of I equals 1 to n of I squared is theta of n cubed. Right. And we also did I equals 1 to n of log I, and we saw that was theta of n log n. Okay, n log n. So maybe we can kind of come up with a guess for these ones. We know the sum of just the I is I squared. So we notice that in this example, we got an extra copy of that n popping out, it looks like. Well, in this example, we also got an extra copy of n. It didn't show up inside the log, it came up out front. So maybe here, a good guess, and here I am just guessing, trying to build my intuition, I might say, hey, this one might be n squared log n. I get an extra copy of n. The sum on the outside gave us an extra copy of n. We've got a guess for what we think this bound might be. Let's see if we can prove it. In fact, the upper bound is not going to be that hard, so I don't need to try too much. I log I is still an increasing function, so we can still over approximate every term by swapping out the I for the n. So let's go ahead and do that. And again, after this step, our term no longer depends on I. That's the intention. So we can move it out front, leaving a very simple sum, which again gives us an extra n. That's what our guess was. Oops, I wrote a 3 there. Let's make that look more like a 2. N squared log n. And again, that's sufficient for our big O, and maybe that's all we're concerned with. A lot of the time that is all we're concerned with. So we get n squared log n. Okay. Now again, if that's all we're concerned with, we're done. Otherwise, we'll continue. Now, for the next one, I'm going to use the same technique, the splitting the sum and binding the term, but I am going to make it a little bit easier on myself because, frankly, I don't like writing so much. Maybe you don't like writing so much either, and maybe you want to have a means of saving yourself a little writing. Now, one thing I don't want to write a lot, because I know it's shown up in all our examples so far, this floor of n over 2 plus 1, floor of n over 2 plus 1. I feel like I've written it a lot already. I'm going to have to write it some more. And it's going to show up here in this I and in this I. I don't really want that. So instead of using the floor of n over 2 plus 1, I'm going to use a technique we're always able to use. Oops, I put a 1 here, but this is fine because what I really want is a k here. I want the value that I'm starting off at k. Now what is k? Well, maybe I'll put over on the side here. K is the floor of n over 2 plus 1. Okay, now I don't need to write it over and over and over again. Let's continue with our approximation then. We've split the sum where? I haven't really said, but it's at k. Over here I said what k was. So the next step, I'm going to swap out for k. All right, so now we have k log k instead of I log I. Again, we can continue now with maybe a little bit of algebra. K log k, I equals k to n of 1. All right, now what this sum is equal to, let's take it one step further. We're going to get k log k times, now we need to be careful here, this one's going to be n minus k plus 1. Okay, n minus k plus 1. Remember, upper bound minus lower bound plus 1 more. All right, now we probably need to write all the nastiness back in there. So let's go ahead and do floor of n over 2 plus 1. That was the first term out front. That's my first k. Okay. Now, log, floor of n over 2 plus 1 here as well. Okay. And then this next term. Well, this one, I'm going to maybe cheat a little bit. I know I've got my floor of n over 2 plus 1 here. That's going in for my k. Well, then the minus 1 that comes out of that cancels with my plus. And I've got n minus the floor again. Oh, well, that's that sum we've already seen a few times. So again, if we've already seen it, we maybe know that that's the ceiling of n over 2. We still need to get rid of those floors and ceilings. And let's remind ourselves again that the ceiling we can over-approximate away by just n over 2 itself. Next up, we have this one, this floor of n over 2 plus 1. Well, again, the floor of n over 2 is greater than or equal to n over 2 minus 1. The minus 1 and the plus 1 cancel out. So that gives us another n squared, or n over 2 here. And then the same thing inside our log. So we get a log of n over 2. And maybe just for ease, I'll leave this one here. Let's see, we're going to get an n squared over 4, I guess, log of n over 2. And of course, we could bring the over 2 out if we want. It'll create a lower order term. But this should be sufficient, at least for our budding intuition, to see that this is an n squared, or a big omega of n squared of log n squared log n. That matches our upper bound here. So we now have an upper and lower bound that match. So again, we can be confident that this our proof is tight now, we have an n squared log n sum. Our sum is bounded in this theta class. All right, that brings us to the end of our 3 examples. I want you to maybe take this away and practice on your own. Consider a couple more general cases. One sum you might want to consider is the sum of I to the power d, okay, or maybe the sum of log to the power c of I. These 2 sums are similar patterns to the one we just seen, and once you have another tool in your tool belt telling you this, I could give you any one, or you could look at any sum of this form and you should know what a good guess for the answer is. All right, if you have guesses for the answer, feel free to let me know, and I'll share my thoughts on the issue. Otherwise, I'll see you in the next video.